Okay, so last time we were looking at the classification of Riemann surfaces which had the upper half plane as the universal covering space, okay, and if you remember, let me recall, we had the following cases. So let me write them down. X, a Riemann surface with universal covering space U. So U is the upper half plane, which is a set of all complex numbers Z such that imaginary part of Z greater than 0. So we have the picture, we have the following picture. This is X sub univ, which is the universal covering space. This is U, and here is the covering projection, and here is X. And as you know that if I fix a point Z here, which goes down to a point X here, then we have an identification of the fundamental group below with the deck transformation group above. So you get this identification pi1 capital X comma small x, the fundamental group of capital X based at small x. You have an identification, namely an isomorphism of groups with the deck transformation group of this covering. So is a deck transformation group of this covering map. So I will just put the covering map, I will just write it as P for convenience. I will not write the whole the source and the target, okay. And this is a subgroup of the automorphic holomorphisms of the universal covering space U, which as you know is identified with PSL 2R, okay. So these are Mobius transformations for the form Z going to A Z plus B by C Z plus D with A B C D real numbers, real entries, okay, and AD minus BC equal to 1, right. So now there were 3 cases. So of course case 1 was the trivial case, X simply connected. If X is simply connected, then the fundamental group is trivial, and X to X, the identity map itself is a universal covering. Therefore by uniqueness of the universal covering, X has to be isomorphic to U itself, okay. Then pi1 X comma X is 0, X is isomorphic to U. This isomorphism is holomorphic isomorphism, is biholomorphic to U. Case 2 was X, so we had 2 possible cases, okay, apart from case 1. That is, we found that when the fundamental group, if it is not trivial, then it is an infinite cyclic group, okay. And there were 2 cases, namely it consisted of only parabolic transformations, okay, and the other case was that it consisted only of hyperbolic transformations, okay. So pi1, so the second case is when deck transformation group. So the point is that this is isomorphic to Z, okay, or 0, okay. The fundamental group has to be either Z or 0, okay. That is what we proved last time. And so if the deck transformation group consists of parabolic transformations, parabolic elements. Mind you, these are Mobius transformations that fix that are automorphisms of U, so they are Mobius transformations in here, and they have only one fixed point in the whole extended complex plane, right. So so in this case what we found was that the universal covering x sub unip to which is U to x p can be identified with U to delta star, okay. So there is an identification like this, so there is a biholomorphic map like this, there is a biholomorphic map like this, and this map is just given by Z going to e power 2 pi I e power 2 pi iz, okay. So this is this is what you get if the deck transformation group contains only parabolic elements, and of course once you identify the universal covering with this, then the deck transformation group of this covering is the subgroup of is identified with a subgroup of translations by a single non-zero complex number, okay, which in this case we have taken as 1, right. So you can see that this delta star is just U modulo Z, okay, it is delta star is just U modulo Z, and of course Z is the fundamental group of delta star, is isomorphic to the fundamental group of Z delta star, okay. So we saw this case, then we looked at the other case when the deck transformation group consisted only of hyperbolic elements, okay. So deck P consists of only hyperbolic elements, so there is an assumption that I have forgotten to say. Of course I am assuming one more important thing that I must recall. I am assuming that the fundamental group of X is abelian, okay. So I should also write that somewhere here, assume, so let me write this here, assume pi 1 x comma x is abelian. This is a very important assumption. It is only because of this assumption that you get these two distinct cases, because you know that a parabolic element cannot commute with a hyperbolic element. So the moment one element is parabolic and the deck transformation group is commutative because it is isomorphic to the fundamental group, then every other element has to be parabolic, and the moment the deck transformation group contains one hyperbolic element, again all other elements commute with this hyperbolic element will force that all other elements are also hyperbolic. So the important thing is you get these two distinct cases because you have assumed pi 1 is abelian, okay. And in this case what happens, so in this case it was there was something that one needs to check, which I will try to do in this lecture. So you see you have the deck transformation group, so you know you can identify X with delta sub R, okay. So you can identify the whole this whole covering map with the following map, okay. And what is this following map? So let me write this, so you know maybe I use okay, so let me not use so let me tell you what delta R is. Delta R is the annulus, open annulus with outer radius 1, inner radius small r, where small r is a real fraction, okay. So delta R is the set of all Z in C such that R is strictly less than mod Z strictly less than 1, and this is for R in 0 1 the open unit interval in R real numbers, okay. Delta R is this annulus, alright, and you see the map here is Z going to so let me write out the formula. It is Z going to e power let me check for a minute. So it is Z going to e power 2 pi I e power 2 pi I log Z by log lambda, okay. This is the universal covering map, where what is this lambda? See the so this the deck transformation group of X, I mean the deck transformation of group of the cover. So let me write delta R, and of course I fix a point, let us fix a point say X, okay, in delta R, right. The deck transformation group turns out to be exactly the infinite cyclic group generated by a single hyperbolic transformation, okay, and that is given by Z going to lambda Z, okay, where lambda is greater than 1, lambda is a real number, right. So this is how we had the deck transformation group. It was just well, so let me write this is the set of all sigma power n, where n is a integer, and sigma power n is just sigma composed with itself n times, okay, and of course sigma power 0 is to be taken as identity, and sigma of Z is just lambda Z, lambda times Z, this is multiplication by lambda, where lambda is real, lambda greater than 1, and this lambda is related to this R in the following way. Lambda is just e power, so there is a formula for lambda, it is e power minus 2 pi squared by log R, okay. There of course I mean ln R, okay, natural logarithm, right. And of course this thing can also be written the other way. I can write R equal to e power minus 2 pi squared by log lambda, one can write it either way, alright, it is one and the same, right. So this is how the universal covering looks, I mean this is how the covering looks if X is a Riemann surface with deck transformation group containing only hyperbolic elements, okay, and isomorphic to Z, right. And so I was making this remark in the last lecture that if you take different R's, then the corresponding annuli, they are not biholomorphic, okay. So that is what I would like to explain why, okay. So that is what I would like to do. So let me do that. So what I am going to do is so consider so you have this map, consider the map, so from 0 1 which is inside R to, well, the set of all possible of all such delta R, okay. So maybe I write such that R belongs to 0 1, okay. This is a set of all these annuli, mind you all these annuli are open subsets of the complex plane, so they automatically inherit a complex structure making them into Riemann surfaces, okay. And of course topologically the fundamental group is just Z, and what is this map? This is just sending R to delta R, okay. This is the natural map, and well, by definition this map is a bijective map, alright. This is by definition a bijective map, and what I am now going to do is I am going to follow this up. I am going to go mod biholomorphisms, that is holomorphic isomorphisms. Okay, so what I will get here is I will put the square bracket here, where this square bracket of delta R denotes the holomorphic isomorphism class. Okay, so send every delta R to its holomorphic isomorphism class, and well you see therefore I get a map like this. Okay, I get a map like this, and the claim that the delta R's are all different for different R is the same as saying that this map is actually bijective. Okay, see this map is already surjective because this is a bijective map and this is a surjective map. Okay, and therefore the composition is certainly surjective. If you say that delta R1 isomorphic to delta R2 implies R1 equal to R2, then you are just saying that this map is also injective. Okay, so the claim is that or rather the theorem is that delta R1 biholomorphic to delta R2 implies R1 equal to R2. Okay, in other words, R going to biholomorphic, that is holomorphic isomorphism class of delta R is bijective. Okay, so this is the claim, right? So we can prove this by using our technique of using covering spaces. Okay, so as follows. So what we will do is let me draw another diagram. So what we will do is let me start with I will start with an isomorphism, holomorphic isomorphism delta R1 to delta R2, and I will prove that R1 equal to R2. Alright, I will do that. Okay, so so proof is start with a biholomorphic map phi from delta R1 to delta R2. Okay, start with the biholomorphic. Okay, we will have to prove that R1 so it's a bijective holomorphic map, injective holomorphic map which is also surjective. So the inverse is also holomorphic, it's a holomorphic isomorphism, and I will have to deduce from this that R1 equal to R2. Okay, and how does one do that? So so let me draw this this kind of diagram. So I have, so you see I have U, okay, which is a universal covering. I have let me call this as P1, covering projection for delta sub R1. Okay, and on the other hand I also have U, I have P2 which is a covering projection for delta R2. Alright, and I have this isomorphism which is phi. Okay, now compose, so what I will do is let me fix a point Z1 in U. Alright, and let us assume that Z1 goes to say x1 here. Alright, and let me take let phi take x1 to x2. Okay, so phi will take x1 to x2, which is a point here. Alright, and I fix a point Z2 in U which goes to x2. Okay, so you look at the order of things that I am doing, the order in which I am doing this. You know, the reason I am doing this is because I need to identify the fundamental group below with deck transformations above. Okay, and so I have to fix a point below. Okay, and so if I fix a point here I get a point there. Okay, and I have to fix points above which go to these points. Okay, of course I do have some freedom in choosing these points because there could be more than one choice. There is more than one choice for this, there is more than one choice for this, but let's fix one choice here and one choice there. Alright, now what is going to happen at the level of fundamental groups? So you see the first fundamental group of delta R1 based at x1, you see that is going to be identified via this map P1, so let me write that, via P1 because of this covering P1 with the deck transformation group of P1, okay, and the deck transformation group of P1 is is sitting inside the holomorphic automorphisms of U, right. So this is what you get, this is the diagram that you get corresponding to this cover, alright. Then you also have a similar diagram for this from the first fundamental group of delta R2 based at x2 to you have an isomorphism, group isomorphism because of the covering P2, okay, and this is going to identify the deck transformation group with the deck, this is going to identify the fundamental group below with the deck transformation group of P2, which is again holomorphic automorphism, I mean subgroup of holomorphic automorphisms of U, alright. And what is notice, I mean going by what I have given here, okay, the you see the deck transformation group of P1 is just given by sigma 1 power n, where n is an integer, and where sigma 1 of z is lambda 1 of z, okay, alright, and lambda 1 is real, lambda 1 is greater than 1, and of course R1 is related to lambda 1 by this formula, so lambda 1 is e to the minus 2 pi squared by log R1, okay. Okay, right, and similarly I have the formula for the deck transformation group of P2, it is going to be generated by sigma 2, so it is all possible compositions of sigma 2 with itself in sigma 2 to the n, where sigma 2 of z is lambda 2 times z, lambda 2 again in R, lambda 2 greater than 1, and lambda 2 given by e to the minus 2 pi squared by log R2, okay. So this is what we get for corresponding to these two covers, right. Now what you must notice is that if I take this covering map and follow it by this isomorphism, I get another map like this, okay, and what is this map? It is P1, it's P1, so let me write it here, it's P1 followed by phi, okay, and this diagram commutes, okay, and this continues to be a covering map, this is still a covering map, because this is just this is a biholomorphic isomorphism and this is a covering map, okay, so the composition is still a covering map, alright. And now because of this covering, what is going to happen is that the fundamental group of delta R2, delta sub R2 based at x2 is going to get identified as a subgroup of or holomorphic automorphisms of this U, okay, namely it is going to get identified with the deck transformation group of this cover, okay. So I will have one more so I will have also something like this, I will have an isomorphism here, identification here. Now this identification is because of this covering phi circle P1, so this is via phi circle P1, okay, and this will identify this with the deck transformation group of phi circle P1, which is also going to be a subgroup of holomorphic automorphisms of U, okay. So you have to keep So the way the fundamental group is identified with the deck transformation group depends on the covering, okay. So this covering, for this covering you have an identification of this fundamental group with the deck transformation group of this covering, which is a subgroup of holomorphic automorphisms of U, okay. The point is that these two are subgroups of the same, these two are being considered as subgroups here, alright. So the first thing I want to make, the statement I want to make is, you see there is a covering maps have a unique lifting property, okay. So you see I have this map phi circle P1, that is a map from U to this, okay. So I can lift this to a map like this, so I will get a map there exists a unique lift which I will call it as phi circle P1 tilde, okay. That is, this phi circle P1 tilde is the lift of this map to U, okay, and of course it is a lift, so this diagram commutes, alright, and this lift will be an isomorphism, okay. This lift will be an isomorphism, that's quite easy to verify, okay. This lift will be an isomorphism. In fact you can check that it will be a holomorphic lift, okay, and it will be injective, okay. So phi circle P1 tilde will be a holomorphic isomorphism from U to U, okay, and since it is a holomorphic isomorphism from U to U, it is going to be a it is going to be a Mobius transformation, it is going to be a Mobius transformation, it's an element of aught U, okay, the holomorphic automorphism of U. I will call this as B, let me call this Mobius transformation as B, okay. Now you see, let's look at only this part of the diagram, okay, let's look at only this part of the diagram, and let's again analyze this. Of course I could have anyway, so let me rewrite it. So I have the following thing, I have pi1 delta R2 based at x2, and that is so I have this isomorphism, this identification, this is via phi circle P1, it is identified with the deck transformation group of phi circle P1, alright, and well I also have the another identification, this is via P2, it is identified with the deck transformation group of P2, well, and both of them are sitting inside the holomorphic automorphisms of U. And then see this commutativity of this diagram, okay, the commutativity of this diagram, what it tells you is that if you give me a deck transformation here, if you give me a deck transformation of this cover, how do I produce a deck transformation of this cover? It is just by conjugating by B, okay. Namely, if you give me a deck transformation of this covering, okay, then so it is an automorphism of U which respects the fibers, alright, and how do I get, given an automorphism of U which respects these fibers, okay, how do I get an automorphism of U which respects these fibers? What I do is I apply B inverse, I apply that automorphism, then I apply B, that is how I get an automorphism of this covering from an automorphism of this covering. So all I am trying to say is that there is a map like this which is an isomorphism, okay, and this map is simply give me any deck transformation for this cover, you get a deck transformation of this cover simply by conjugating by B, okay. So you have a map A, so this map is just A going to B, A, B inverse, okay. So in other words what I am trying to say is that I am just saying that and this diagram of course commutes, okay, this diagram of course commutes, and this is just the statement that if you change a covering by an isomorphism, by an isomorphic covering, then the Deck transformation group will change by a conjugate in the group of holomorphic automorphisms of the universal cover, alright. So what this tells you is that it tells you that B dot Deck phi circle P1 dot B inverse, which is the image of this, is actually Deck P2, that is what it says, okay, you get this. But what I want to say is, I just want to say that this is exactly the same as the Deck transformation group of P1, okay. So the claim is LHS above is exactly the same as the Deck transformation group of P1, okay. And why is that so? That's because of the way the identification of the Deck of the fundamental group is because of the way you identify the fundamental group with the Deck transformation group. So let me explain that. See, I guess I should put in fact I should put B dot this dot B inverse, and my claim is in fact actually the claim is that this group Deck phi circle P1 is the same as Deck P1, okay. I mean so what I am just saying is that the Deck transformation group of this cover and of this cover are the same, okay. I am saying the Deck transformations group are both, I am saying these two these two are equal, actually these two are equal here, okay. So how does one do that? So if let's try to recall the way we got the Deck transformation. So what we did was, you see I have see I had this point, I have this point x1, so this is the point x1, and here is the point z1 above, alright. And what was the map from the first fundamental group of delta sub r1 based at x1 to Deck transformation of P1? What was this map? So you see this is the map P1, alright, and what was this map? So you see I took a homotopy class of a loop alpha starting and ending at x1, okay. So I took something like this, okay, and then what I did was I took its, so this is alpha, I took its unique lift above, I got a unique lift alpha tilde because of the unique lifting property, and that gave me a new point here. That point also was a point lying over x1, so I got a new point alpha tilde of 1, okay, and it was the Deck transformation that this alpha defined was a unique Deck transformation that takes z1 to alpha tilde of 1, that is how it was defined, and that is one and only one, okay. So this is just the unique Deck transformation that sends z1 to alpha tilde of 1, alpha tilde being the unique lift of alpha, okay. Now in the same way, how do you get an identification of pi1 of this with the Deck transformation group there, okay. So let me write that down, pi1 of delta r2 comma x2, okay, to the Deck transformation group of phi circle P1, okay. How was this done? This was done in the following way, namely what you did was, well, you had x2, a point in delta r2, alright, and then you had this point z1, and z1 is being mapped to x2 by this by phi circle P1, because P1 takes z1 to x1 and then phi takes x1 to x2, alright. And what did we do? Well, this is the map here is defined by, well, you send beta to the unique deck transformation that that sends z z1 to beta tilde of 1. So namely what you did was you took a beta here, homotopy class, and then you well lifted it to a beta tilde. So it is a little cramped, let me try to draw a slightly better diagram. So so here is z1 and I had this beta tilde which is the unique lift of beta starting at z1 for this map for the covering phi circle p1, okay, and this ended at a point. This point is also going to lie over x2 for this cover, okay, and this point is beta tilde of 1, and the deck transformation you are getting, the automorphism of the upper half plane you are getting is the one that is the unique one that sends z1 to beta tilde of 1, okay. Now notice that, you know, note that if phi of alpha is beta, okay, namely I'll put in this diagram here, so there is also x1 here and there is also alpha here. Suppose alpha goes to beta under phi, under the isomorphism phi, okay, then it is very clear that the lift alpha tilde of alpha under this map which is p1, okay, is the same as beta tilde which is lifting under this map. After all, well, alpha tilde is the lift of this, okay, and therefore it is also a lift of beta, alright. So beta tilde and alpha tilde are one and the same, right. So the moral of the story is that you know, the image of this inside the holomorphic automorphisms of U, which is the deck transformation of the covering P1, is exactly the same as the image of this in the holomorphic automorphisms of U, okay. So this implies that, you know, the deck transformations of P1 are the same as the deck transformations of phi circle P1. The deck transformations as these two groups are one and the same inside the group of holomorphic automorphisms of U, okay. Well, so that proves the claim, okay. Now therefore you see, so what I can do is in this here I can replace this by deck of P1. So finally what I get is deck P2 is conjugate of deck P1, alright, by B. So deck, so B dot deck of P1 dot B inverse is the same as well deck P2, okay. These two are one and the same. Now you see, you take this element sigma 2, this is generator of B2, okay. This has to correspond to an element here, okay, and that element being here, it has to be of the form B1 sigma B sigma 1 power n B inverse. That is how elements here look like, okay, because elements in deck P1 look like composites of sigma with itself, alright. So but you see, this is a group identification, right, and the generator has to only go to a generator, okay. Therefore this has to be either sigma 1 or it has to be sigma 1 inverse, okay. There are only two possible generators, it is an infinite cyclic group isomorphic to Z, there are only two possible generators. So this has to be sigma 1 or sigma 1 inverse, okay. So the moral of the story is that the upshot of all this is that either sigma 2 is equal to sigma 1 or sigma 2 is equal to sigma 1 inverse, okay, that is what you get. Now what does that lead to? So let me write here, okay, I think I can rub off this and continue. So well I will get, so you see I will get so sigma 1 or sigma 1 inverse is sigma 2, this is what I get, alright, and well I think I should be a little careful. I should either say I should conjugate by B, yeah. I should be careful. B sigma 1 B inverse, or not exactly sigma 1 but or B sigma 1 inverse B inverse. I should be careful because if sigma is a generator of this, then B sigma B inverse is generator of the conjugated mode, okay. So so let me make that correction. So sigma 2 is either B sigma 1 B inverse or sigma 2 is B sigma 1 inverse B inverse, okay. Now what is sigma 1? See, sigma 1, if I write it as a matrix, alright, it is sigma 1 of z is lambda 1 z, so it will be root lambda 1 0 0 1 by root lambda 1, okay. So this is what sigma 1 is, okay. Sigma 1 inverse is going to be, well 1 by root lambda 1 0 0 root lambda 1, this is how I write representatives in SL2, alright, and well the same works for 2 also, so I will just put subscript I, okay. So I will just put I here, okay, and now compute the trace. So what you will get is trace squared sigma 2 is going to be the trace squared sigma 1, or is going to be trace squared sigma 1 inverse, okay, depending on whether it is equal to this or that, because you know under conjugation trace is not going to change. If you write this, so if you write this down, what you will get is, you will get if you take both cases, you will simply get lambda 1 lambda 2 plus 1 by lambda 2 plus 2 is equal to lambda 1 plus 1 by lambda 1 plus 2, okay. And if you solve this, alright, what you will get is, well you are going to get lambda 1 is equal to lambda 2 because both lambda 1 and lambda 2 are greater than 1, okay. So what you will get is, well lambda so this will imply lambda 1 is equal to lambda 2 as lambda 1 comma lambda 2 are both greater than 1, this is what you will get. And if lambda 1 is equal to lambda 2, you will get R1 is equal to R2 because R1 is just e power minus 2 pi squared by log lambda 1, which is equal to e power minus 2 pi squared by log lambda 2, which is equal to R2, okay. So thus we get that the inner radii of these annuli are one and the same, okay. And the beauty is to see that we have applied diligently covering space theory to prove this, okay. So this implies R1 equal to R2, so I should say delta R1 isomorphic to delta R2 implies if and only if, so I put so R1 equal to R2, okay. So this clearly tells you why two annuli with different R's, they are not going to be biholomorphic to one another, okay. So so I think that clarifies to some extent the remarks I made towards the end of the last lecture, okay. So we will stop here.